Sorry about that. Technological glitch. Like I said, we're going to use these basic differentiation rules to do some examples. So, if you would like, once you see the problem, you could pause, try to do it on your own, and check it with me. If you're a little bit lost and you just want to see me do it, you can watch. I'll be explaining. First one, 2 sine x dx. So we want to identify what rules we're going to use initially. So this would be constant multiple rule. Constant multiple is 2. So we can put a 2 up front, do a rewrite. We're looking for an indefinite integral, the antiderivative of sine x. 2 is 2. I know it has something to do with cosine, but the derivative of cosine is negative sine, so I need another negative there. So when I differentiate this, the two negatives will make the positive here. And then lastly, plus c. Don't forget your plus c's. Combining that without parentheses, negative 2 cosine x plus c. There you go. Constant multiple rule. Next one, let's do something a little different. Identify the rule. It's sum rule. This is a polynomial. The sum rule allows us to do polynomials term by term. So a rewrite would look like this. I don't expect that you'll do this every time, but the first time we'll do it. In other words, the sum rule, you can distribute, so to speak, that integral. So first term plus the integral antiderivative of the second term. And now you go to town. Hopefully we've done this one enough today that you know it's 1/2 x squared. And it's a plus c, but this one will also contain a plus c, a different c, and the constants can be combined into one constant at the end. So the derivative of what is 2? That'd be 2x. And then let's combine those constants into one big one called c. Just like derivatives, sometimes a rewrite is the way to go. And here's an example of that. That's not really in a good form to take an antiderivative of, because you're thinking the derivative of what gives me that. Not a good form. So let's do a rewrite here, and rewrite will probably involve dividing both of those terms by square root x. So this is x to the 1, that's x to the 1/2, and let's divide right there. So to do that, we subtract exponents. So 1 minus 1/2 is 1/2. And then we can use sum rule on this. 1 over root x, that's 1 over x to the positive 1/2, so bring that to the top. It's going to be an x to the negative 1/2. Now that we've got our rewrite, we can use our power rule for antiderivatives, indefinite integrals. First of all, this one. Add 1 to 1/2, you get 3/2. And then we need the reciprocal of that out front. Add 1 to negative 1/2, we get 1/2, and the reciprocal of that is 2. Plus c. Do not forget that. You could check all this by differentiating, and we should be able to verify the result. Might have to add some fractions together. I'm doing that in my head. Looks good. Last one, keeping the trig going. Sine x divided by cosine squared x dx. Once again, we're thinking backwards. The derivative of what gives you that? That's kind of messy, so we're going to do a rewrite. Let's group sine and cosine together. One sine and one cosine. And then there's going to be 1 over cosine left over. Sine over cosine, also known as tangent. And 1 over cosine, also known as secant. So now, hopefully, if you've done your memory work, you know the derivative of something is secant x times tan x. And hopefully you know that that is secant x. So sometimes with trig we want to rearrange group and we'll get something familiar. This being the familiar thing. Alright, so first objective was to find antiderivatives that follow directly from derivatives of basic functions. So that's what we've done so far. And we've been working with the general. General has the plus c. Now I'm gonna give you one more piece of information and you'll be working on coming up with specific, sometimes called particular solutions. In that these ones, this stands for infinity different solutions, but we want the specific c is what we're gonna find. Here we go with that. I'm glad my eraser erases so awesomely. So this part you could do so far. Find the general solution of this differential equation. Derivative equals 1 over x squared. But here's the difference. And find the particular solution that satisfies f of 1 equals 0. This we call an initial condition. It's a point on the original. Notice that this is the derivative, but this is the original. So we're going to see how all of that works. So first of all, we want an f of x. Not f of 1, we know what that is, but we want f for all x. So we've got to solve this differential equation, and how to go from a derivative to a function is an antiderivative. So we did it on the left side, so we want to do it on the right side. Now I'm thinking a rewrite there. 1 over x squared. That's the same as x to the negative 2. Use our power rule. We want to add 1 to that and do the reciprocal, which is negative 1, and then a plus c. So our general solution seems to be negative 1 over x. Of course we could differentiate that. I'm checking that in my mind. Seems to be good. So take the left and the right side, that collapses into our f of x equals negative 1 over x squared plus c. Now, here's the difference. We want to use the initial condition to solve for that c. Or, another way to say it is, we want to force this function to go through that point. So, f of x is going to get a 0 as x gets a 1. X is 1. The y is 0. So, that has been substituted in. Carry out that and solve. It's easy to see that the c is 1. Now I can write a particular solution. F of x equals negative 1 over x plus, now I know the c is 1. So that is going to fulfill both of these things. This initial condition, plug in 1, you get out 0, but also if you differentiate it, you get 1 over x squared. So we've got a specific function, a specific solution, particular solution, you might say.